Okay, sorry for the delay in this. I've just been getting more and more work put on my plate here throughout the morning, but I'm only about an hour behind schedule, so I apologize for that. But here is, as promised, the torque walkthrough example video. So yesterday we did this PowerPoint, so I'm just going to quickly zip through it as a quick reminder to set the stage for the example problem we're going to be doing here in this video. So torque, all about spinning, twisting, turning, a sort of force that causes an object to spin in a circular motion rather than to just move. So torque is all about spinning, twisting, and turning. We looked at various examples of torque. We talked about the pivot point being the point of rotation. So the object moves around the pivot point, such as the center of a windmill, or a bolt for the wrench, or maybe the middle of a merry-go-round, or a knee on your leg. All of those are examples of pivot points where an object will spin around that point um, in some sort of circular fashion. We looked at the torque equation, which is equal to the perpendicular force times the radius, or the distance to the pivot point. And so here we saw that force B would have more torque because of that increased distance. We're cruising along here because we saw all these notes yesterday. So you can check the recording from yesterday's class. That would be 12.1. And you can check that recording from yesterday's class if you want more detail on these notes. The main point of this video is the example problem at the end. So net torque, just like net force, you add up all of the torques together, keeping in mind that if you're spinning one direction, it's positive. If you're spinning the other direction, it's negative. And you get to choose which way is positive or negative based on the problem. So if you look at the problem and you're like, counterclockwise makes sense for positive on that problem, then you can go ahead and say counterclockwise is positive, and that would make clockwise negative. Then you might have a different problem where it's spinning the other way, and it makes more sense to call clockwise positive and counterclockwise negative, and that's fine too. Just make sure you keep it the same for the whole problem. You can't have it one way at the start of the problem and then flip it halfway through the problem. So just like when we could decide, left is positive or right is positive for the x direction, you can decide that for circular directions as well. You just have to make sure you keep it consistent. Right hand rule, I'm just going to completely gloss over because I've decided next year I'm not even going to teach this. I tried to sneak it in there as a little college preview, and I don't think it worked super well. It's really hard to teach the right hand rule in remote because you guys can't really see what I'm doing with my hand, which is kind of the whole point of the right hand rule. So long story short, just forget about the right hand rule for now. It's not going to be on the final. It's not going to be on anything. I was just trying to give you guys a little advanced knowledge there, getting ready for college, and I don't think I did a very good job, to be perfectly honest. So just forget about the right hand rule for now. Practice problem, this time with some actual numbers. And we got that the combined torque from these two forces added together. So that one was pretty straightforward. We then talked about what happens if there's an angle, and we got this equation here that if you're not at a perfect 90-degree angle, then you need to use the sine to figure out how much of that force is perpendicular, right? Just like when we took an angled force and split it into an x part and a y part, same thing here. We're taking an angled force and getting just the perpendicular part. So in order to do that, we need to use sine. So you take the whole force multiplied by the sine of the angle. And interesting to note here, the sine. Sorry about that. I forgot I'm not on OneNote here, so I actually have to click the button in order for my pen to pop up. Sorry about that. But if we have the sine of 90 degrees, this really should go on the previous slide, but I accidentally tapped and made it skip ahead. But the sine of 90 degrees equals 1. So that's why technically it's the same formula for all angles, even a perfect 90-degree angle, because when you enter that sine of 90 degrees, it just becomes 1, right? So that formula for your perpendicular force times sine of the angle will always work, even if your angle is a perfect 90 degrees, because sine of 90 degrees is just 1. So then you get force perpendicular equals the entire force, right? So sorry, I tapped the screen a little too early. I'm used to working in OneNote, and now I'm working in PowerPoint. So that should have gone on the last slide, but I just wanted to remind you guys that sine of 90 degrees equals 1. So then our overall torque equation becomes force times the distance to the pivot point, the radius, times sine of the angle of the force. Right? So we've got, so that's our full equation for torque that takes into account the strength of the force, the length of the radius, and the angle involved. So in this case, we have all of those things, right? In this example problem, we had a force, we had a radius, we had an angle, and we plugged it all in to get an answer, right? So we got our force times our radius times the sine of the angle to get the total torque. And I'm sorry, my scribbles have overlapped that. So let me just move this over here. That our full torque equation is equal to the force times the radius, or the lever arm length, times the sine of the angle of the force. All right, scooting along here. This is the part we haven't gotten to yet. This is so I'm going to slow it down here and really go step by step. So here's the situation. We have a shelf that for some reason isn't screwed into the wall. Yeah, it's being supported instead by a wire. So we've got a wire supporting this shelf, and we need to know the strength of the force applied to the shelf by the wire, right? So at first glance, the word torque hasn't shown up at all yet, right? So we're like, okay, this is a force problem, a free body diagram problem, cool. Unfortunately, though, because of the circumstance, we're not given enough information to do this as a force problem. So let's first try to do this as a force problem, and I'll show you where the problem occurs, right? So if we drew a regular free body diagram for this shelf, then obviously gravity is attempting to pull the shelf downwards. The wire is supporting the shelf at this angle here of 25 degrees. So we've got a force from the wire there lifting the shelf up. And then we also have a frictional force from the wall itself, right? Because the shelf is touching the wall right here, right there. So the shelf is touching the wall, so we've got some friction, and the shelf is touching the wall, right? So when two things are touching, that also creates a normal force. So the wall is pushing out against this shelf a little bit as well. So here's the issue. We know force gravity, right? Because we've got 5 kilograms, so we know that force times gravity, 5 times 9.8. So we know force gravity, and we know the total net force, right, is 0 because this shelf isn't accelerating. It's attached to the wall, so it's not going anywhere. So no acceleration. So all of these forces do have to balance out. The problem becomes we don't know what force normal is, so we don't know what force friction is. We don't know what the coefficient of friction is. We don't know what the strength of the wire force is. There's just too many things we don't know here in order to solve the problem like this in using a free body diagram like we're used to, right? We don't know this. We don't know this. We don't know this. That's too many things we don't know. And we also don't know this, right? So we can make an x direction equation and we can make a y direction equation, but we would need 4 equations in order to solve this problem, right? Because we have 4 things we don't know, and we need an equation for each thing we don't know. So we have 4 things we don't know, and we really can only make 3 equations, right? We could with it. So we don't have enough information to solve this using our normal forces techniques. However, we do have enough information to solve this using torque. So Let me erase this here so it doesn't get in the way of the actual stuff. But I just wanted to show you that yes, indeed, this is a torque problem, even though the word torque didn't show up in the problem, right? It says force. But we can see, looking at the picture, that we have a pivot point here, right? Where if this wire were to snap, then all of a sudden this shelf would fall down and slam into the wall. So actually we are going to assume that this shelf is screwed into the wall, but that itself is not enough to support the whole weight of the shelf. So this wire helps support the rest of the weight of the shelf, right? So you can see how this becomes a torque problem because we have a pivot point, we have a radius, right? The shelf itself is our radius. And if this wire were to break, the shelf would start to spin in a clockwise direction. So now you're starting to see where this is a torque problem instead of just a regular forces problem. So your pictures, your diagrams, I always say this, your diagram is going to be your best friend on these physics problems. In this situation, there are two torques acting on the shelf here. So obviously the wire is applying a torque, right? Because it's got a force of some force we don't know yet at a radius of 0.35 meters, right? So there's the torque from the wire going up in the counterclockwise direction, and then the weight of the shelf itself, right? The force of gravity is pulling down on the shelf in an attempt to spin the shelf in the clockwise direction, right? So the weight of the shelf itself, the force of gravity, creates some torque as well, right? So if we think about it in terms of the pivot point here, gravity is trying to spin the shelf this way, and the wire is resisting gravity by holding it up this way. So those are our two torques that are in balance right now, right? Because the shelf isn't actually spinning. The shelf is attached, it's stable, it's not spinning clockwise or counterclockwise. It has no net torque. So we know that the gravity torque and the wire torque need to balance out. So there's something I like to call a torque free body diagram. So rather than just having a box, you need a line, right? So we've got this torque free body diagram here that shows both of the torques acting on this shelf. And you can see here that we've got gravity trying to push it down and spin it in the clockwise fashion. And the wire is keeping gravity from doing so. The wire is supporting the shelf and keeping it held up. So your question might be, wait, but what about force normal, right? We had force normal against the wall. So why isn't that applied? You know, why don't we have to worry about force normal? Well, here's the thing. Force normal happens here, right? Force normal occurs where the shelf touches the wall. The radius at that point is 0 because that is the pivot point. It's 0 meters away from the pivot point there, right? So there's actually no torque from that force, from force of friction or force normal, because both of those forces occur at the pivot point. So it doesn't matter how much strength the force has, the radius is going to be 0, and therefore the torque is 0. So any forces that occur at the pivot point itself have 0 torque because there's no radius, there's no distance, right? So when we plug our R into the torque equation, we'll get a 0. So by looking at this using torque instead of force, now we only have 2 forces to worry about instead of 4. So we made this a much more simple situation mathematically by using torque instead of force, because the shelf is only experiencing 2 torques, even though it had 4 forces. So that really helps us even things out. Force of the wire, we don't know. We know the angle is 25 degrees, but we don't know what the force of the wire is. That's the goal, right? So I'm going to write that on here. This is the goal. We want to know what the force of the wire is. In order to do that, we need to know what the torque from gravity is, so that way we can also figure out what the torque of the wire is. The torque of the weight, the torque from gravity. Now, if you have a symmetrical shelf, so in this case, we're going to assume that the shelf is symmetrical, that this side doesn't weigh more than this side. We're going to go ahead and say that it's a uniform shelf. So the density and weight and everything is same throughout the whole shelf. So the left half of the shelf will have an equal weight to the right half of the shelf. And because of that, we can just go ahead and assume that because of symmetry, we can assume that all of the weight balances out to the center of the shelf. So you can treat force of gravity on an object like this as a force acting just like this diagram shows here, a force acting directly on the center of an object because of that balance, because the left side and the right side are balanced, and so all of that weight mathematically can be thought of as right in the middle. There's that. So now let's solve the problem. Right? We have a lot of information here. Let's solve the problem. This is something I like to call a torque free body diagram. It doesn't even need all of this picturing to it. Honestly, if I were to draw a torque body diagram for a problem like this, I would simply draw it like this. Here's my pivot point. Here's my shelf. I've got a force torquing it this way and a force torquing it that way. And that's my free body diagram. Okay, so it's no longer just a box because we now care about force and distance. So we have to show all of that information on our free body diagram. We need to show the forces with the arrows, but also the distance, right? The radius from the pivot point. So these torque free body diagrams show that. They show the location of the pivot point. They show the forces involved. And they also show the distance, right? Because now distance matters. That is a torque free body diagram. So now that we have a free body diagram, we can set up the equation, right? So in this case, net torque is going to be the torque of the wire in the positive direction and the torque from gravity or weight in the negative direction, right? Because we said counterclockwise is positive. That's what we decided up here. So that means the wire is trying to go up in the not up, but counterclockwise in the positive direction. Gravity is opposing that force, going in the negative direction. Gravity is trying to go clockwise. So just like we just discussed, we subtract the torque from weight because it's going in the negative direction, which is clockwise. So again, like we mentioned before, since the shelf is being held up, we know it's not twisting. So it's not twisting up, it's not twisting down, it's perfectly balanced, just like Thanos likes it, right? So perfectly balanced. Because of that, we know that there is no net torque. Net torque must be zero because it's not spinning. The shelf isn't spinning clockwise or counterclockwise. Very similar to when we had forces, right? And there was no acceleration. If there was, and we would know that net force is zero because there's no acceleration. Same thing with torque. If there's no spin, then net torque is zero, and that means all your torques are balanced. So what does that mean? It means the torque of the wire and the torque of the weight must be balanced out. They must be equal to each other. Now it's time to figure out what torque of the wire we can't figure out torque from the wire yet because we don't know the force from the wire, but we can figure out the torque from gravity. I apologize, my animations got a little messed up. These things aren't supposed to show up quite yet, but that's okay. So let's plug in what we know, right? So we know that torque of the wire equals torque from gravity, torque of the weight. So now let's plug in our torque equations here. So torque of the weight is simply going to be the force of the weight, which you can see right here is 49 newtons, and multiplied by the distance. And remember, we said that weight, gravity, can be assumed to be in the middle, the exact center of the shelf. So since the shelf is 0.35 meters long, the middle of that shelf would be 0.35 divided by 2 meters long. So that's where that comes in here. That's where this divided by 2 here comes in, is because our gravity force is in the middle there. My animations got a little out of order here on this slide. I apologize. I was like, shouldn't I have something in between those? So yes. So you can see, right, that torque is equal to force times radius times sine. But for gravity, we don't need to worry about the sine because it's already a perfect 90-degree angle there, right? So we don't need to worry about sine for gravity because it's 90 degrees. It's already perpendicular. For the wire, we don't know force of wire yet, so we're just going to leave that as force of wire because we don't know what that is yet. Sine of 25 degrees because that's our angle, 25 degrees. And you can see I've given you that information here already, sine of 25 degrees. And the radius for the wire is the full 0.35 meters, right? Because the wire is attached at the very edge of the shelf. Gravity is symmetrical, so we put it in the center of the shelf, which is why we had to cut that radius in half. But the wire is on the very edge of the shelf. So position, location matters for torque. Location matters a lot, right? Force times distance. So distance is half the game here. And so the distance for the wire is the full 0.35. The distance for the force of gravity is half that, 0.35 divided by 2, which would be 0.175. So now we can multiply all those things together. And that's what we get there. So I just multiplied on the left, I did 0.423 for the sine. So 0.423 times 0.35 gives us that 0.148. And on the right, 49 times 0.35 divided by 2 gives us 8.575. So now with a quick division, we can figure out what the force of the wire is, which is 57.939 newtons, right? So we use torque here to find a force, and that's a very, very common application for these sort of things. Suspension bridges, right? You may have seen a suspension bridge before, like the Golden Gate Bridge, the very famous one. So Golden Gate Bridge, here we are, something like this, and here's the road, and it's being supported. It obviously has some supports underneath it, but it's also being supported by these cables, right? It's a suspension bridge, so these cables are helping hold the bridge up as well. So those cables apply a torque just like the wire on this shelf applies a torque. And they do these exact same types of calculations on the bridge to make sure that the bridge is not too heavy, to make sure that the wire is actually strong enough to hold up the bridge when it's full of a bunch of cars. Okay, my bird loves physics. Anyway, so that's where you would use these types of problems in real life, is making sure that your wires are strong enough to hold up your ski lift chairs or your bridge or your telephone cables, whatever it is, anything that's being supported by a wire or any sort of shelf-like situation, these torque calculations are done to make sure wires are strong enough to hold things. So for example, let's say this wire was rated for 100 newtons. Well, in that case, this wire will work just fine because it's only going to be feeling about 58 newtons. Now, let's say this wire was rated to hold 50 newtons. Now, well, that would be a problem, right? Because this wire, which is the company only guarantees up to 50 newtons, is going to be holding something that's 58 newtons. So yeah, it'll probably be okay, right? But you're taking a risk there. So that's usually how this works, is your wire is rated to hold an X amount of force, and you need to do this torque calculation in order to make sure that the amount of force the wire will be holding is less than the maximum allowable amount of force. So that's where you would see a problem like this show up in real life. The next assignment, which I'm going to roll out tomorrow, we'll have a chance to practice some problems like this. And then I have a challenge assignment for some bonus points. Certainly nothing that's going to be on the final or anything like that. But if torque can get way complicated, and so if you'd like to see some examples of that in action, then you can take the torque challenge, and the torque challenge is all about situations like this: bridges, and basically a bridge is like a shelf but with two sides, and so your pivot point, instead of being on the side, your pivot point is going to be in the middle in that situation, which means that this wire is trying to go counterclockwise and this wire is trying to go clockwise, and it can get pretty complicated, as you might imagine. So the homework that everyone has to do is just things like this, like the shelf, the problem we just practiced. But if you would like to challenge yourself for some bonus points and take a look at some of these, Golden Gate Bridge type situations, then absolutely, I have that worksheet available, and I would love for you to challenge yourself like that. So just let me know what I can do for you, and I will see you guys in class tomorrow, where we will continue to practice this torque concept together. But I wanted you to see how torque works in real life. It's not always just about opening doors and turning screws. Torque shows up everywhere, even when something's not moving at all, right? Like a bridge. We sincerely hope the bridge never starts spinning. That would be really bad. But it's still a torque situation because it has forces and radius, and everything's trying to balance out in a circular fashion rather than in a linear fashion. I hope you guys found this helpful and somewhat enjoyable, and I'm going to get to work on that energy lab. I apologize again for being a bit behind schedule today. So have an awesome day, everybody.